Okay, I'm back, and now we want to do a review of Interlude D, the Earth's Interior Revisited, Insights from Geophysics. And so what we're going to be looking at is the thermal properties of the Earth, the gravitational properties of the Earth, the seismic properties of the Earth, and then the electrical and magnetic properties of the Earth. So this is going to correspond to Interlude D in your textbook. And the first thing we want to mention is what did we know about the inside of the Earth during the early 20th century? So when we've only dug into the Earth a distance of like 5 miles. So that's as deep as we've gone inside the Earth. However, the size of the Earth is thousands of miles in diameter. So how do we know what's inside the Earth if we can't physically touch it? Okay, so here's some things that we know about the Earth. So one is, what is the overall composition of the Earth? So we know that the Earth is composed of certain elements. And we think that's true because the Earth formed from the collisions of thousands and thousands of asteroids. So if we know the composition of an asteroid, and we know that because we found meteorites here on Earth, now we know what the overall composition of the Earth is. Okay, then since we assume that the Earth came from asteroids, we can measure the density of a typical asteroid and then say that that's the density of the Earth. Okay, the next thing is we need to know what the size of the Earth is. And so the ancient Greeks were able to measure this like 2,000 years ago. Don't worry about how they did it, okay? Just know that we know what the radius of the Earth is. Okay, then the next thing is we can figure out the mass of the Earth. So if we know the volume of the Earth, so the volume is V, and then we know the density of the Earth, which is rho. Density is equal to mass divided by volume. So we know the rho, we know the V, so we could solve it for M. So now we know what the mass of the Earth is. Okay, then the next thing is, how do we know how hot it is on the inside of the Earth? Well, a lot of it's guesswork, but we know that the energy that would have been produced by the collisions of all the asteroids that made the Earth. We also know that the Earth would be hot due to radioactivity going on inside. We also know that additional energy would have been released as the iron fell to the core of the Earth. And then we also know, though, that the Earth is radiating heat back into outer space. So, a lot of theory, but we think that we know how hot the inside of the Earth is. Okay, what about pressure? So the idea is that the deeper you go inside the Earth, there is going to be more material on top of you. So the weight of all of those rocks pushing down on top of you is going to cause pressure. And so we can calculate the pressures inside the Earth. Don't worry about the formula, but just know that we have a pretty good idea of how the pressure changes from the surface of the Earth down to the core of the Earth. Now, we want to predict what kinds of rocks would exist at those different levels inside the Earth. And now this is going to be based on chemistry. So in chemistry, if you know the pressure, and if you know the temperature, and if you know what chemicals you're working with, the composition, you can calculate what kind of chemical reactions would take place and what kinds of rocks would be present. It can be done. So that's all I want you to know. And then finally, we know that the Earth has an iron core because it would have gotten so hot that the iron would have flowed to the center of the Earth. And we know that metallic materials can generate electricity and magnetism, so that we now know that the Earth has a magnetic field on the inside of it. So here's our summary of all of that information. So the Earth has a iron nickel core. It has a mantle composed of dense rocks, and then it has a crust composed of not so dense rocks. But with the advent of seismic waves generated by earthquakes, we were able to figure out that the Earth has also additional layers on the inside of it. So if you recall, there were two kinds of seismic waves, the S and the P, and that the S waves, the P waves were going to be faster because of their primaries, and the P waves could travel through liquids, but the S waves could not. So remember, that's what you need to know for the test. Don't worry about those formulas there. Another thing that these waves can do is they can be reflected. So you should know the definition of reflection. So it's when light hits a surface and bounces off of it, and then notice that those two angles are equal to each other. You should also know what refraction is. So refraction is going to be the bending of a wave when it goes through something. And so as earthquake waves travel through the Earth, they are going to bend when they encounter different layers inside the Earth. You should also know what the MOHO is. So the MOHO is the Mohorovich discontinuity. And so we're just going to say the word MOHO, and that's going to be the boundary between the crust and the mantle. And then the way that we discovered this was by observing the speeds of the S and the P waves in those different layers. Okay, then we also discovered the mantle. So the mantle is going to be the layer underneath the crust, and we mapped the different layers in the mantle by observing the speeds of the S and the P waves as they traveled through the mantle. Okay, then we've got the core mantle boundary. So we figured out where the core mantle boundary was because the S waves were stopped by that boundary. So the P waves were able to travel through the liquid outer core, and they appeared on the other side of the Earth. But the S waves were stopped by that liquid outer core. So the fact that the S waves cannot penetrate the liquid outer core allowed us to locate where that boundary was. Okay, then you've got the inner core. So the way that we discovered the inner core was that those P waves were able to penetrate the outer liquid core, and then some of them bounced off of the inner solid core. And then we observed where they went, and then from that we were able to figure out the size of the inner core. Another thing you should notice is that notice that the inner core is solid, but the inner core is actually hotter than the outer core. So you might think that the inner core should be a liquid, because you know that when you heat up something, it turns from a solid to a liquid. Well, it's a competition between pressure and temperature. If temperature is winning, then a substance is going to be a liquid. If pressure is winning, then that substance is going to be a solid. And so we know that the deeper you go inside the Earth, the temperature increases, and so does the pressure. Well, it just depends on which one is winning, whether the rocks inside the Earth end up being a liquid or a solid. So what can we learn about the inside of the Earth in addition to all these different layers? Well, we've also noticed that as these earthquake waves are traveling through the Earth, they are going at different speeds depending on whether they're going through solids or liquids. So they're going to be going faster through solids than they are through liquids. And so this allows us to actually measure, using earthquake waves, the temperatures inside the Earth. And so we can actually map convection cells, places where material is going up and material is going back down, based on the speeds of earthquake waves as they travel through those materials. Okay, we could also use earthquake waves like sonar in order to map layers at the surface of the Earth. And then we could use that in turn to hunt for ores, for example. All right, let's take a break. When we come back, we're going to talk about what does gravity tell us about the inside of the Earth.